I'm Linda Parker Gates, and I lead the SEI Software Acquisition Policy and Practice Initiative, and I'm also the principal investigator for AI Robustness. And presenting with me this morning is Dr. Nicholas Testa. He's up here in the front row, and Nick is a senior data scientist with our software engineering measurement and analysis team. So we're going to talk to you this morning about potential problems with AI, particularly with AI and ML performance over time, and explain how a tool that we have called AIR, it's actually a methodology and a tool, can be used to sort of examine your predictions capabilities and ensure that they're working the way you want them to. And then we will give you an invitation to work with us, because we are looking to work with as many different kinds of projects and programs as we can. So in a nutshell, AI and ML, as you know, are revolutionizing prediction capabilities, but classifiers are subject to limitations that are caused by things like concept drift and data drift and emerging phenomena, edge cases, things like that, that can inject bias into a classifier's predictions. I really enjoyed some of the things Alexis talked about this morning in terms of bias. It is sneaky, and so that's why we talk about AI and ML performance over time, because things can start to happen, and if you you might not be aware that bias is being injected, or you might be aware and start to lose confidence in the predictions that are important to you and that you're basing decisions on. So this tool helps us examine AI and ML results really with more confidence. So you may have seen this picture before in this example. It's an example of a kind of bias called survivorship bias. And the situation that this illustrates is one where Allied military aircraft were returning from combat during World War II, and the planes were being analyzed for damage, basically to see how well they were performing. And if you look at this picture, you might conclude that the wings and the tail and the center of the body were where a lot of the hits were occurring, and so maybe those are places where planes need to be reinforced. But in fact, if you realize that you're only looking at planes that returned, there's a blind spot associated with the planes that did not return. Okay, so that bias it's known as survivorship bias, because the bias comes from the fact that you're looking only at surviving planes. If you look at all planes, you might learn that these are actually pretty well reinforced areas and things where you're doing pretty well. And so you don't want to make decisions based on something that has bias in it, because you could end up treating the wrong things. So really, to be effective in critical problem spaces, which I think we are all working in critical problem spaces, classifiers need to be robust. They need to be able to produce accurate results over time and across a range of scenarios, because scenarios change too as you use your tools and the things that you are trying to make decisions about. So overall, we just need to be careful about the way we are caring for all the idiosyncrasies associated with the tools. So I want to talk a little bit about correlation, because AI and ML rely heavily on correlation and sometimes don't account for some underlying causal structures. And we're going to talk a lot about causal learning this morning. But basically, what's wrong with a little correlation? It's good for quite a bit, right? But heavy reliance on correlation can lead to models that don't allow you to look at alternative explanations or fail to account for some key drivers that might be attributing causes to the wrong factors. And there are some kind of fun examples, like around the dangers of correlation, like if you were to correlate falling asleep with your shoes on with waking up with a headache, right? But we could probably guess that there's a common cause for both of those things, and it's not the falling asleep with your shoes on that causes the headache, right? So in this example, you'll see that the probability of mission success increases with mission complexity. It's a little curious, right? I'm not sure that would be my guess, but and so you might want to look closer at that. It turns out that if you add a third variable about experience level of the people executing the mission, the data flips, and your correlation becomes exactly the opposite. Mission success is correlated with the simplicity of the mission. That's one way to say it. But it is, in fact, not correlated with mission complexity. So this phenomenon is called Simpson's paradox, and it's kind of one where the total data skews when you look at it in a superset rather than in terms of some of the things that may be underlying. So we need to be aware of these different kinds of bias. The SEI's body of work in causal learning is probably close to a decade old, and has led us to a fairly sophisticated solution for examining AI robustness that uses some state-of-the-art algorithms in causal discovery and causal inference, and teases out causal structure and gets us away from solely relying on correlation. So Nick is going to introduce a scenario, and he's going to talk through our methodology and give you an example. And then I'll be back.
All right. Hey, everyone. I'm Nick Testa, so I'm the data scientist on the team. So I'm going to take you through an example that we're using to explain how the new tool that we built, the AIR tool, the AI Robustness tool, use this example to introduce the tool and take you through how it works. So in this example, we have a unit within the DoD being tasked with deploying unmanned aerial vehicles to acquire images in various locations of interest. So they have two bases available to the team. So we have a home base and an away base, or rather an auxiliary base. And they want to be able to predict mission success, which is being able to acquire images from either the home or auxiliary base. And they want to know which base has the highest likelihood of success. And that's what we're trying to predict. So mission success here is acquiring images. And the experimental variable is the main base choice. So naturally, this team built a series of ML classifiers to predict mission success, and then they want to keep the best performing one, but they notice maybe the classifier seems to produce biased effects sometimes with the main base choice, and they want to figure out why. So our demo, our client knows many of these mission parameters, maybe things like mission urgency or region sensitivity, can affect things maybe like which base is chosen and also mission success. So we already know we have some confounders. Additionally, we know things like the environment at each base, maybe like altitude, temperature, humidity, these kind of things can affect success in other ways. So we want to understand not just what mission success looks like based on which base is chosen, but also why. So some of these unrelated events may end up changing the environmental variables enough that the classifier performance starts to degrade, and we want to be aware of that. So naturally, we needed to build a tool to account for this and understand whether or not this AI classifier might be producing biased results. So our new AI robustness tool was the answer we came up with. This makes heavy use of a field called causal learning, which is a form of machine learning that focuses on identifying and understanding the cause and effect relationships within the data, as opposed to simply identifying the correlations and making predictions on those. So causal models represent assumptions about how variables interact to produce outcomes and are used to infer causality and answer questions such as, how did the data come to be the way they are, and what data are driving which outcomes? It helps us formally answer the question of, does X cause Y, or is there some other reason they seem to co-occur together all the time? So let's say we have these two variables, X and Y, that are obviously correlated. Humans are very good at looking at this kind of data and assigning causation. So first X happens, then Y happens. So clearly, X causes Y. So first, we choose which base to take off from. Then we measure mission success. And we see maybe a change. So clearly, choice of main base, choice of which base to take off from causes mission success to increase. But how do we test this formally? Until recently, there was no formal language or methodology for testing causal questions like this, which is where we get the age-old mantra, correlation is not causation. But this is where causal learning comes in. So it helps us tackle problems of identifying things like Simpson's paradox or survivorship bias, which in this case may be occurring here, which is what makes them look so similar. There's a lot of cool science in here, so as we go through this, just keep in mind, I have a very visual way of thinking about things. I'm a little bit of an artist, so amateur. So if you see these main base is always going to be represented in this light gray color, and that's our experimental variable, and the mission success is going to be in this kind of dark red. So as we follow through the presentation, just keep in mind the experimental variable is the light gray, and the outcome is the dark red. There are some other color matching that you may see as we pull the threads along, but just keep in mind that I like to do that kind of stuff. So causal learning is the tool that we're using to quantify the robustness of the AI classifier. So this provides an explicit framework that allows us to do things like build causal diagrams, account for bias and confounders, and estimate the magnitude of effect on unexplored scenarios. In our example here, it helps us understand that main base and mission success maybe have a common cause, like mission urgency, which can inform both which base is chosen and also mission success. And this can be a source of bias that we want to correct for. Causal learning allows us to do that in a quantifiable mathematical way. So there are two main fields within causal learning. So we have causal discovery, and this allows us to build cause-effect graphs, so causal graphs or diagrams from the data. And we have causal inference, which uses a pre-existing causal graph to estimate the effects of an intervention or an experiment. So in this case, the choice of base that we use. Causal inference can be then further broken up into causal identification and causal estimation, which allow us to identify sources of bias and then quantify the impact that experimental variable might be having. Causal estimation is ultimately the thing that we're after. So what makes our tool unique is that we can start with the data and build out a causal graph with causal discovery, identify potential sources of bias, and estimate the effect with the bias removed. So our tool allows you to calculate the what-if scenario of what if we were to remove all the effects of bias from the model. What would the outcome look like then? What is the true effect that the base selection has on mission success? And does it look any different from the model that we currently have? And if so, why? To do that, we need this end-to-end causal learning scenario, or rather tool, sorry. And I'm going to take you through kind of how that works. So the first step, like I mentioned, is causal discovery. So this allows us to take our data along with what we call a knowledge file and some parameters to generate a most likely causal graph. So the AIR tool applies state-of-the-art algorithms for causal discovery to output a most likely causal graph, and this can be improved by using that knowledge file I mentioned earlier. And so all that is the data. So we have the data file here. So these are all the different variables that go into this. So these are the variables, the features that are used in our machine learning model. The knowledge file is these variables rearranged and separated into groups based on how we expect causation roughly to look. So on the top, we have exogenous variables, those that are unlikely to receive any causal input from anything below them. On the bottom, we have variables that are the inverse of that are likely only to receive causal information and not give it. And anything in between is kind of a hybrid, able to give and take causal information from anything else on the board. We can subset this even further if we have the subject matter expertise, but it's really not super necessary. The causal algorithms that we use are robust enough that that this is sufficient. But we're just going to use these for now. Okay, so back to that original question. How does our choice of which base to take off from affect mission success? So this is kind of the graph that we were starting with, right? So this is where we know that we have bias. is that we already have something like mission urgency. After we put our data into the tool, we can see there's more than one place where bias can be introduced, potentially. And this graph expands. So I've gone ahead and shrunk everything in the environment down into one node, because for our purposes here, that's all we need. I'll go ahead and show you the full graph later, so don't worry. So unfortunately, we can't take this graph straight into the causal inference step just yet. Anytime we see variables with common causes like urgency has on region and environment, we know that that can introduce bias. And we want to account for that, because just downstream of region and environment are main base and mission success. So we can already see a path from main base to urgency to mission success. And this is a place where bias can be introduced because they're both common causes, and we need to account for that. And so this is one of the ways that we account for this bias, is by using causal learning to break the kind of connection between the paths that we don't want, so that we can just focus on the path from main base to environment to mission success. Causal identification is this next step that allows us to tease these apart. So we break this off into two adjustment sets, is what we call them. And so this allows us to look at parents of the main base as one adjustment steps, and parents of the environment, which as another. So the environment is kind of the intermediate in between main base and mission success, and that's what we're after. So these two color-coded groups here kind of allow us to break the connection between main base and mission success in all of the alternate paths that we don't want bias from. And we can then take these and input them into causal estimation algorithms later, so that we can calculate the effect that main base has on mission success for both of these different color-coded sets. So now we're finally here, and remember, the goal is to use cause-effect relationships to answer the question, what if? So what if we had the same data but changed the scenario, main base? So instead of taking off from the main base, we're taking off maybe from the auxiliary base for all the individuals. What effect does that have on our outcome, mission success? Well, to answer that, we apply a non-parametric, doubly robust estimator, which is a targeted maximum likelihood approach. We're using that to discover the optimal treatment and outcome model for each adjustment set, and the result that this gives us is both a point estimate for the risk difference in mission success, and also a 95% confidence interval for each of the adjustment sets. So ranges like this basically correspond to the upper and lower limits of how big an effect we expect our our experimental variable to have on our outcome. If everything looks good, these ranges aren't too dissimilar. We can then compare with the average treatment effect, or the risk difference rather, predicted using existing AI classifiers. So assembling this final output requires that the predicted risk difference of the original classifier be calculated, plotted alongside the causally derived confidence intervals. And so this position of this AI classifier, this original classifier that we built to determine whether or not that choice of main base, of how it affects mission success, is what we're after, is that position. So the resulting causal intervals here provide two independent checks on the behavior of the classifier on this use case of interest. If one set is violated, this might be a fluke, but it's worth keeping an eye on. If both are violated, however, the consumer of the classifier predictions should be wary of these predictions for that particular use case, knowing that it is likely biased. And so these two adjustment sets, the two adjustment sets that we have these confidence intervals for provide recommendations on which variables or features to actually look at for subsequent classifier retraining. So pulling all of this together into one, hopefully easy to read output, we have a mock-up of the Air tool results window. So we have the causal graph on the left, and that shows us the experimental variable, scenario main base, on the left, or well, highlighted in yellow, and then also images acquired, which is the outcome variable highlighted in yellow. On the right, we have a risk difference figure that shows that the existing classifier is outside both causally derived confidence intervals. So each of the variables that make up those adjustment sets are then highlighted in red on the causal graph on the left. And so those are the mission urgency and region sensitivity. So it turns out that for both of these variables, we are introducing some bias in the current model, and we need to look at those and investigate them so that we can deal with this bias. So, Linda? Take our time.
Still standing? We are sort of a late stage project here in our research program, meaning that the math itself, the science is pretty well baked, and we are in a stage where we are trying to transition this capability outside of the SEI, which is really exciting. Now, if you talk to the mathematicians, there's always work to do, but we are trying to get your participation in this project at this point now. And so hopefully you can see the value in using this end-to-end causal learning solution in this kind of a context. But causal learning has very broad applicability, and AI is everywhere. So the playing field on this is really huge, and we're actually learning that the more people we talk to. We hear about a lot of different domains and scenarios and types of data sets where people think this might be useful. So if you heard anything today that speaks to you, please come talk to us. If you're using AI classifiers to make predictions or to make important decisions, if you are wondering if your classifiers are performing well, and if you have just some time to offer, we kind of can come to you prepaid, if you will, because this is funded research. So we aren't looking for the typical kinds of engagements where we have to ask you for money. As part of our transition effort, we have worked to put this tool into, really to pull the human elements out of it and put it into a containerized state so that people can easily use it. It is right now fully automated and fully containerized. We have some data set requirements that we would need to talk about, and the data sets need to be of sort of reasonable quality, but those are all things with fuzzier lines around them. So if you're interested, please do contact us. We have a poster, and a table over in the other room. We'll be here all day. We would be excited to talk to anybody who has an idea, even if it's longer term. We've had some folks ask us about use of LLMs and image data, which we aren't quite at, but we are thinking about those things. So anything you're thinking about, we'd love to hear about. And I will just. There's a QR code, but really if you come to see our poster, you can get the same information, but feel free to snap a picture of that. That'll lead you to a lot of materials on this project. And I want to close by sharing our very large team. I was thinking about Alexis's talk this morning. We're at the point where this knowledge is not me or me, or we, it's us. This is the group of folks who are contributing to this work. Everybody brings something to it that is unique and valuable for the technology, the tooling, the transition. A lot of us are in the room today, and I think I have a couple minutes, Tom, to answer some questions. So if you have some questions, let us know, and I or one of my colleagues will answer it.